Okay, so we're skipping 2.4, just so you know. That's not part of the AP curriculum. So we're going to go to 2.5 and 2.6 today. Okay, there's a lot of terminology in this lesson that you guys got to be familiar with. Okay, the first thing that we're going to talk about for a little while is continuity of a function. Okay, so I'm just going to go through this one box at a time. So let me start with an easy way to understand what it means for a function to be continuous. And so the easiest way to think of what a continuous function is if you can trace over it without ever lifting your pencil. Okay, then you can say the function is continuous. Is that clear? It's the easiest way to think about that. Okay, and another way I want you to start thinking about a function being continuous is that it has no holes, no breaks, no jumps, and you can also add in no vertical asymptotes. Okay? Okay, so again, a function will be continuous if it has no holes, no breaks, no jumps, and no vertical asymptotes. Okay. Now, how can you talk about continuity of a function using calculus concepts? Well, that's what's coming next. Okay, so a function will be continuous at any and all x values a only if, okay, listen closely, this limit equals f of a. Okay, now what do I mean by that? Well, first of all, notice this is a two-sided limit. In other words, as you approach a from both the left and the right, the y values have to be approaching what? What's f of a? F of a is the actual what? Y value at a. Is that clear? So that's the formal definition of what it means for a function to be continuous, okay, at a, okay? So, again, the limit as x goes to a equals the y value at a is another way of looking at that. That's exactly what that says. Now, obviously, for f to be continuous at a, both the limit and the f of a value have to exist. If either of them don't exist, then obviously f won't be continuous. So not only do they both have to exist, but they have to equal each other. Is that clear? Okay, so the following three situations show how a function is not continuous, or in other words, discontinuous at a. Ready? Okay, the first situation, why is this function not continuous at a? Because there's a what? Well, there's a hole. Now, what does that mean using calculus concepts? That what? That f of a is what? Not defined at a, right? Okay, so in other words, f of a is not defined. Okay, this you can think of as a, well, I refer to it as a break, but I think the book might refer to that as a jump, but it doesn't matter. You know, the bottom line is you recognize that as being a discontinuity. Does that make sense? Okay, and again, the reason I like to call it a break is because obviously the graph is broken into two separate pieces. That's why I like to call it a break, but whatever. All right, now how can you communicate that type of situation using calculus? By saying what? The two-sided limit does not exist, right? And why does that represent a situation where the two-sided limit does not exist? Because from the right and left, you're going to two different what? Y values. Does that make sense? Okay, so there's that. And then the third scenario is that in this case, does the two-sided limit exist? Yes or no? Yeah, it does. What is it? The y values are approaching what? 2, from the right and the left. So the limit does exist. It's 2. However, f of a is up here at what? 3. So even though the limit exists and even though f of a exists, they are not equal to each other. So that's a third situation where a function would be not continuous or discontinuous at x equals a. Does that make sense? Okay, now I'll add that fourth situation, and that is what? If there's a what? If there's a vertical asymptote at a, obviously that's another scenario where the function will not be continuous at A. Make sense? Okay? Okay. All right, so let's look at an example. Okay, we're starting out with a piecewise function here. And I want to talk about whether or not that function would be continuous at x equals 3. All right, ready? Okay, so what do we have to prove or show? Well, what do we need? We need three things. We need to find the two-sided limit. We need to find the y value, right, at A, and then we need to figure out if they're equal to each other. So those are the three things we have to look at, right? Are you ready? All right, so first of all, we have to, in order to find the two-sided limit, we're first going to find these one-sided limits. Does that make sense, guys? We're going to find these one-sided limits, and once we find those, I can get the two-sided limit, which is the first thing I need. Is that clear? Okay, so how do we find the limit from the left here? By using which piece of the function? The top. Okay, now remember, all you got to do is plug in the 3 there to get the left-sided limit, because whatever the y value is on that square root, that's what you'll be approaching as you approach 3 from the left. So if I plug a 3 in there real quick, what do I get, guys? Square root of 4, which is what? 2? Okay, now, how about from the right? How about the right side limit? Well, coming in from the right of 3, you're going to use the bottom function, aren't you? Yes? And since the y values are always 2, obviously they're going to be approaching what? 2. So everybody agree that that's the right-sided limit? So what do you think? If the right and left-sided limits are the same, what's the value of the two-sided limit? 2. Okay, so far so good, right? We've got the two-sided limit existing at equals 2. Now what do we got to find next, guys? What are you going to find next? The value of f of a, right? In other words, I got to find f of 3. Well, what is f of 3? Well, which piece of the function do I use at 3? Well, because of that equal sign, I use that function to find the value of f of 3. Is that clear? And so what is it when I stick a 3 in there? What do I get? 2. Okay, so what do you think, guys? The two-sided limit exists as x goes to 3. F of 3 exists, and they're the same. So what does that mean? This function is what? Continuous at x equals 3. Make sense? Are we good? All right, here's another one, another example. So again, if I give you a function and you want to show or figure out whether it's continuous or not at x equals 1 in this case, what do you need to do? You need to find the what? The what? First you find the what? The two-sided limit, and then you find the value of f of a and see if they are equal to each other. Okay. Now this is different. Look at these. For all x values except 1, which piece of the function am I going to use? The top part. Okay, so if I want to figure out the limit as x goes to 1 of this function, then I need to figure out what the value is, right? When I plug in the 1. So what do I get when I plug in the 1? 1 over 0, which is, well, we don't know what, right? We're stuck, right? So, but what did we say last time? When you run into a non-zero over 0 scenario, then this limit is either going to be infinity, negative infinity, or does not exist. Okay, so coming in from the left of 1, like if I put in 0.9, what do I get? Oh, wait, stop right over. You know what? I don't even need to go there. Let's just do this. Do you agree it's going to be one of those three things? That limit's either going to be negative infinity, infinity, or does not exist. Do you agree? But are any of those a number? No. So right away you can say what? It's not continuous. Because why? Since the two-sided limit, what? Does not exist. I mean, it might be infinity, but, or negative infinity, but those aren't numbers, right? It's got to be a number, right? In this case, doesn't it? In order for it to equal f of a, doesn't it have to be a number, right? So right away I can stop. I don't even have to check anything else, do I? Okay? So this function is going to be not continuous at x equals 1, since that two-sided limit is not going to exist. It's not going to be a number. Okay? Make sense? Okay. Now, you guys just listen closely. This sounds confusing, but if you pay attention and just let me get through this, it's not too bad. Okay, I'm only going to do one example. You might have one example on the homework, and that's about it. So, anyway, let's look at it. What's different about this box than what I've been doing? This is talking about continuity at specific x values, right? Now we're going to talk about continuity on an entire interval. Does that make sense? Okay, so a function f is continuous on an interval a to b if it is continuous at every number between a and b, and it is continuous from the right of a and from the left of b. Now, what in the world does that mean at the end? Well, continuous from the right of a means you only have to make the limit from the right equaling f of a. Okay? In other words, here's a. As I come in from the right of a, do those y values. In other words, does the limit equal the f of a? That's what it means to be continuous from the right of a. Does that make sense? And then on the other end, we're going to talk about being continuous from the what? Left of b. So what that means is, do these y values, as you get closer to b, in other words, does that limit, does that one-sided limit approach and equal the actual y value at b? That's what I mean by continuity from the right of b. Are you following me? Okay, so in order for a function to be continuous on the whole interval, okay, got to be continuous from the right of a, like I just explained, from the left of b, right? And f has to be continuous at every other x value in between a and b as well. Does that make sense? Okay? All right, so, okay, this example might seem repetitive, I mean, as far as the steps go, but I do technically have to go through all this, okay? So watch what I'm going to do real quick. Please write this down in the space I gave you. Okay, I want to show that this function is continuous on the entire interval -1 to 1. Are you ready? Okay, there's three things I have to show. Number one, that what? That the what? Limit as I approach a equals a for any x value in between -1 and 1. So let's start with that. Are you ready? Okay? All right, so to do that, I got to talk about, in general, what is the limit as x approaches a for any number between -1 and 1. Are you ready? Okay. Okay, looking at 1 minus a square root function. Are there any holes or any discontinuities on or any asymptotes on a square root function if it's defined? Yeah. Sometimes the square root function is not defined. I mean, if you think of a basic square root function, if you look at a basic square root function, obviously it starts at 0, 0 and rises gradually like that. So there are some discontinuities out here, right? However, and so we just have to worry about, and why are there discontinuities over here? Because you can't have the square root of a what? Negative. Okay, so let's think like that. Okay. For numbers between -1 and 1, will this ever be negative? That's my question. Between -1 and 1, will the square root of 1 minus x squared ever be negative? No, it will not. Because when you take numbers between -1 and 1, they're going to be all decimals. If you square them, you still have decimals, right? That are smaller than 1. Then when you subtract them from 1, it's still going to be positive, isn't it? So what I'm saying is then, all you have to do is plug a into there. Whatever a is, as long as a is between -1 and 1, all you can do is plug it in. So if I plug an a in there, then the limit will be just whatever the y value is here, which is what? 1 minus the square root of 1 minus a squared. Does that make sense? Do you understand? It's just going to be that. You're just going to be able to plug in the a values As long as we're talking about a values between -1 and 1, we'll be fine, right? That the substitution will work to find the limit, right? Agreed? Okay, now what is f of a? Well, f of a is the same thing, isn't it? Don't you just plug a in there to get f of a? Don't you? Same thing, right? So what do you think? So do these things equal each other, yes or no? Yes, they do. So far, so good. Okay, keep going. Okay, now I want to talk about the what? The one-sided limit as I approach -1 from the right. In other words, I'm finding this part of it right now. Okay, so real quick. As I come in from -1 from the right, okay, as I approach -1 from the right, okay, okay, so as I approach -1 from the right like that, what kind of decimals am I going to be plugging in? Or what kind of numbers am I going to be plugging in? Decimals that are what? That are negative, but they're going to be to the right of -1. So they're going to be like -0.7, -0.8, -0.9, right? And do you see any problems with those when I plug them into the function? Am I going to have y values at all those on this particular function? Yes or no? Yes, I am. Okay, so what am I saying? So what I'm saying is to find that limit, all you got to do is plug what? -1 into the function. So if I plug -1 into the function, what do I get for the y value here, guys? What do I get? Yeah, because if I plug -1 in there, I get what? 1 minus 1, which is 0. Square root of 0 is 0. 1 minus 0 is what? 1. Okay? So I'm going to have a bunch of y values that are going to be approaching the y value 1. Is that clear? So that's the limit from the right of -1, as we just talked about, correct? I know this seems repetitive, but you do have to think like this. All right, now what about f of -1 itself? How do you find that? Just what? Plug it in. So when I plug -1 in, what do I get? 1. So far, so good, right? Yes? All right, now I got to talk about approaching +1 from the left. Okay? So as I approach +1 from the left, like this, what kind of numbers am I going to be plugging into the function? Some positive decimals, right? And when I plug them into this function, are they going to be defined, or am I going to have problems? It's going to be defined, right? So I'm going to have a bunch of y values, right? And what are those y values going to be approaching, guys? They're going to be approaching what I get when I plug 1 into this function. So again, when I plug 1 into this function quickly, what do I get? 1. All right, how do I find f of 1? Plug 1 in. What do I get when I plug 1 in? 1. All right, so there you go. Since 1, 2, and 3 are all true, then this function is continuous on the interval what? -1 to 1. Okay, guys? Okay? Don't worry. I'm not going to do too much with that. I just wanted you to understand what I mean by continuous on an interval. All right? All right, that's not what most of the examples are going to look like. Okay, so don't panic if that was kind of grueling to get through. All right, so here we go. A whole bunch more terms for you to know, or a whole bunch more facts as well. Okay, so here we go. Let's talk about functions that are continuous, so that we can have a whole list of things that are continuous. Are you ready? All right, the following functions are continuous wherever they are defined. Polynomials, make sense? Those are always continuous where they're defined, right? Rational functions, root functions, trig functions, inverse trig functions, exponential functions, logarithmic functions. Okay, that's a lot of functions, isn't it? All those are what? Continuous where they're defined. Got it? Okay. All right. How about combinations of functions that are continuous? Well, as long as f and g are continuous at a, okay, and by the way, if I ever talk about c is a constant, then the following functions are also continuous at a, right? If you add two continuous functions, you get a what? Continuous function. If you subtract two continuous functions, you get another continuous function. Are you following me? If you multiply two continuous functions, you get a continuous function. If you multiply a continuous function by a constant c, you get another continuous function. If you divide two continuous functions, you get another continuous function as long as the denominator is what? not 0. If you take a composition of functions, f of g of x, you get another continuous function as long as what? G, first of all, is defined at a, and then after that, f is defined at g of a, okay? Okay, now a new term. Ready? What's the difference between a removable discontinuity and a non-removable discontinuity? Ready? Very important. And then we're going to do 2 examples of this, and we're going to move on to something different. So these are the only examples I'm going to do here. So you got to learn these terms and learn them well from these 2 examples. Are you ready? Here it goes. A whole discontinuity is called removable discontinuity, so you can make that function continuous by simply filling in the hole. That's the easiest way to think about a removable discontinuity. If you can just fill in the hole to make it continuous, that would be categorized as a removable discontinuity, because you can fix it with one point. Does that make sense? That's the easy way to remember that. Okay, a removable discontinuity, which again would be just a hole, occurs when you can algebraically cancel out the factor causing the discontinuity. You saw a bunch of examples like that last time, didn't you? Where after we factored or simplified or multiplied by the conjugate, the discontinuity canceled out, right? Remember that? Remember where the denominator was 0, making the whole thing undefined? Remember how it canceled out and then you were able to continue and find the limit? That's what I'm talking about. Okay, and I'll show you another example in a minute. Okay, now, what about a non-removable discontinuity? Well, what falls into the category of a non-removable discontinuity, guys? Think about it. A what? A vertical asymptote or a what? Or a break. Okay, those are the types of discontinuities that would be non-removable if you think about it. Because they can't be what? Canceled out, so to speak, algebraically. Okay, I think you'll see this a little bit better after I do example 4 and 5. You ready? Okay, so write this down, guys. Here's a function. I want you to find all discontinuities. Where will that function be? Not continuous. Whenever the denominator is what? Is what? 0. Doesn't that make sense? You got to figure out when the denominator is 0 here to find your discontinuities, because that's where it would be undefined, right? Okay, so here we go. Factor the denominator, guys. What do I get? X and an X, a plus and a minus. What do I need? Yeah, minus 4 plus 2, don't I? Okay. Now, before you cancel anything out, guys, before you cancel anything out, where's that function not continuous or discontinuous? Where? At -2 and what? And 4. Do you agree those are the discontinuities? It's obviously undefined there, so obviously it will not be continuous there. All right, now, you can categorize these 2 discontinuities as being either removable or non-removable. Okay, now go ahead and cancel out the what? X plus 2's. All right, you see how I just canceled it out? I removed that. So this discontinuity would be what? Removable. Okay, so that one you can label as removable. It's still a discontinuity, though. Don't go telling me on the test that that's no longer a discontinuity. It's still a discontinuity. It's just categorized as a removable one. But it is still a discontinuity. Right? All right. Now, what about x equals 4? Is that a removable discontinuity or is that a non-removable discontinuity? Was there any way to cancel it out there? No. The denominator is still going to be 0 there, right? And so that's what? Non-removable. Okay? Any questions on that one? We good? Pretty easy, isn't it? Yeah? All right. Go ahead and try example 5a, guys. Try it on your own. Don't do B yet. I'll do B with you in a minute, but at least try A on your own. Does the top factor, guys? What does it factor into? You tell me. X what? Times x minus 1. Everybody agree that factors into that? Okay, before you cancel anything out, are there any discontinuities? Yeah, what is it? X equals 1 is a discontinuity on that function, isn't it? Okay, is it removable or is it non-removable? It's removable. Because I can what? Cancel those out. And so it's removable, right? All right, now, let's look at B. Okay, so we started out with this function, right? And I want you to graph it, right? Isn't that what I'm saying in part B, to graph that? All right, well, you probably don't know what that looks like, but watch this. After you simplified it, you got the new function what? F of x equals what? X minus 2, which is a what? It's just a what? It's just a line, isn't it? Following me? Well, so the good news is the graph of that function looks just like the graph of that function, except that there's a what? A hole at what? 1. So if you want to graph this function here, all you got to do is draw the line y equals x minus 2 and put a hole at what? X equals 1. Okay, so there's x equals 1. So by the way, what does the line y equals x minus 2 look like? Well, the y-intercept is what? Negative 2. And then the slope is 1, so you can rise 1, run 1, right? Yes? So there would be a point there, but I'm making an open point, right? Got it, guys? Isn't that what the line y equals x minus 2 looks like, but with a hole at x equals 1? So that's what the graph of this function looks like. Are you following me, guys? Okay. All right, remember I said there's about 5 or 6 major theorems that I'm going to teach you guys? Well, this is the second one already. Okay, what's it called? The intermediate value theorem, which I'll always abbreviate as the IVT. Okay? Okay, now again, when you read this theorem in your textbook, it will not be split up like I split it up. I did that for you to help you understand. So anytime you need to read a theorem on your own in the future, you're going to do exactly what I'm doing here, which is separate it into the if part and the then part. All right? And now, don't even look at the then part. Do not even look at it for a while. Just focus on the if part. And by the way, don't even look at the picture yet. Just start reading. All right? Are you ready? Okay, if. What's the if part of the theorem? If the function f is continuous on the closed interval a to b, stop. Think about what that means. What does that mean? It means no what? Holes, breaks, jumps, or vertical asymptotes. Okay, so start thinking like that. Continue. And n is any number between f of a and f of b. What in the world does that mean? Well, that means, well, f of a and f of b are the what? Starting and stopping y values. Isn't that what you should be thinking of in this case? F of a and f of b are the starting and the stopping y values on the particular interval we're talking about. And then, so then n must be some y value in between those two y values. Does that make sense? You see how I'm slowly reading it and kind of picturing what they're talking about? Okay? So again, let me back up. We've got a function with no holes, breaks, jumps, or vertical asymptotes. And we're starting with some y value n that's in between the y values what? F of a and f of b. So, right? All right, so what I did then is I kind of drew a general example of what that might look like. Okay, so I just drew a random continuous function from a to b, and then I picked some random y value n in between the starting and stopping y values. Okay, so far? Okay? All right. So have I drawn a general scenario where the whole if part of the theorem is true? Have I? Yes, I have. So then the theorem, then the purpose of the theorem is in these scenarios, in these situations, the theorem guarantees that something else will also be true. That's the then part. That's the conclusion of the theorem. So what is the then part of the theorem? In this case, what must also be true now? That there must exist a what? Number C in the open interval A to B where f of C is equal to n. What the heck does that say? Slowly read it. So there must exist a number C in the open interval A to B. That means there must exist an x value, right? Is what it's talking about. In between A and B. Isn't that what I mean by the open interval A to B? In between A and B, where what? Where the what? The y value is equal to the y value n that you started with. You follow me? Again, sounds confusing, but it's not. So what does that mean then? That means if you look at the y value n and you follow it down, there has to be an x value c where the y value is n. That's all I'm saying. So there you go. There's the value of c that must exist according to the intermediate value theorem. All right? Sounds complicated, but it's not. And again, I'm going to state this one more time as simple as I can. What this theorem says is if you got a continuous function from A to B, and you pick a y value between the starting and stopping y values, it's got to correspond to some x value c in between the A and the B. That's all. Got it? Okay, so theorem number 2 out of the way. You only have about 3 or 4 more the rest of the year. Okay? All right. You guys, what do we do with this theorem? Well, I'll tell you right now. This theorem is mostly used to prove the existence of certain x values, right? And that's what I'm going to show you next. I'm going to do one example, and then again, I'm moving on to something different. Are you ready? Okay. It says, prove that the graph of this equation has a 0. And what's a 0? A 0 is just another word for what? A root or a what? X-intercept. So I want to prove that that function has an x-intercept somewhere between what? 2 and 3. And obviously, I want to use the intermediate value theorem to prove that. Are you ready? Okay. So I want to start with the if part. Okay? So here we go. Since, okay, so in order to prove this, I'm going to have to basically prove that the entire if part is true, right? And if that's true, then the theorem will tell me that the rest of it will be true. Got it? So I'm going to talk about the if part. What's the if part? That what? You've got a what? Continuous function. So all I'm going to say is since y equals x cubed minus 5x minus 7 is a polynomial. Isn't it a polynomial? It is continuous on the what? Closed interval what? In this case, what? What's our interval? 2 to 3. Does that make sense? Didn't I say that about 20 minutes ago, that all polynomials are continuous? Aren't they? Think about it. Aren't polynomials continuous everywhere? Right? Okay, so since the graph is a polynomial, or the function is a polynomial, it'll be continuous on the closed interval 2 to 3. Okay, what else do I have to have? What's the other part of the if? I have to be talking about a y value in between what? I have to start with a y value between what? F of A and F of B. What y value am I talking about here? What y value am I talking about? Well, what's the y value on an x-intercept? What's the y value on an x-intercept? 0. So I want to say, and since the y value n equals 0 is between, what does it have to be between? It has to be in between what? F of A, which is f of what in this case? 2. And what? F of what? F of B, which in this case is f of 3. Well, let's see if it is before I go any further. Okay, what's f of 2? Everybody put a 2 in there, quick. What do I get? 8 minus 10, which is negative 2. Don't I get negative 9? Okay, quick, put a 3 in there. What do I get? 27 minus 15, which is 12, minus 7 is 5. What do you think? Is 0 in between negative 9 and 5, guys? Everybody, is 0 between negative 9 and 5? Yes, it is. So by that, the intermediate value theorem tells us that what? There must exist what? Must exist, yep, a y value, I'm sorry, an x value c, where what? So in between what? 2 and 3, where what? Where what? Where what? F of c equals n, which in this case is what? F of c equals what? What's my n? 0. Okay, so there it is. So that proves there's an x-intercept somewhere between 2 and 3. Doesn't it? Okay? Guys, this is not easy, but I try and make it as easy as I can for you to understand, right? Yeah? Do you see what I did? I mean, again, it's a lot of writing, it's a lot of wordage, but there it is, right? Is wordage even a word? I just made up a word, maybe. Okay. Maybe I should have said wording. Okay, but anyway. Good? Okay, are we halfway done? All right, the good news is this page will go a lot faster. That's the good news. Ready? Here we go. All right, before I go any further, okay, I'm kind of changing directions now, guys. I'm doing 2 sections, so I believe this is where the second section begins, okay? Okay, so I'm kind of starting over now. Ready? Okay, before I get into the section, I have to point out a few things with these graphs. Look at those 3 graphs. You guys tell me, looking at that graph, what is the limit as x goes to infinity? In other words, if x is going this way, what are these y values approaching? Yeah, they're approaching that horizontal asymptote, which is 3. And obviously, there's a horizontal asymptote at y equals 3. Are you following me? See the connection there? Obviously. Okay. Look at the second graph. As x goes, again, positive infinity. So look at this. As x goes to positive infinity, the y values are going to be approaching what? 4. And again, isn't there a horizontal asymptote at y equals 4? Again, I want you to see that connection. Okay, here's another one. But this time I'm asking you first for the limit as x goes to negative infinity. So as x goes to negative infinity, here are the y values. What are they approaching? Negative pi over 2. How about when x approaches positive infinity? Well, here are those y values. They're going to be approaching what? Positive pi over 2. And so in this case, I have how many horizontal asymptotes? 2. One of them's y equals negative pi over 2. The other one's y equals positive pi over 2. Okay? So, you see the connection with these limits as x goes to positive or negative infinity and horizontal asymptotes. You see that connection. Okay, that's where I'm going next. Are you ready? So, here we go. So, in general then, the line y equals L will be a horizontal asymptote of the curve y equals x if what? Either of the following is true. When you take the limit as x goes to positive infinity, you get L. Or if you take the limit as x goes to negative infinity, you get L. Obviously, based on what I just showed you in these graphs, that will be the case. Agreed? Easy, right? Okay. All right. Now, I'll come back to that in a minute. I'm going to tie it together with what I'm going to show you next in just a few minutes. But let's go to an example before I do anything else with horizontal asymptotes. Okay, here we go. All right. You guys, I want to find these 2 limits. And by the way, since I'm not going to a number, all those tricks and things I taught you last time won't help us, will they? Because x is not going to a number on those, is it? X is going to infinity or negative infinity. On these types of problems, one strategy to find the limits is by what? analysis. In other words, just think about it. Are you ready? All right, let's do the first one, guys. As x goes to positive infinity, guys, let's talk about this as x goes to positive infinity. Ready? Okay. When x goes to positive infinity, the denominator is going to get bigger and bigger and bigger, right? So I'm just throwing some numbers up there. Guys, what's happening as x gets bigger and bigger and bigger? The whole fractions are getting what? Smaller and smaller and smaller and smaller. So what's the limit? 0. Just 0. I agree they're getting smaller, they're going to 0, aren't they, just by thinking about it? Yes? Okay. So that's where I got that limit from, right? All right, now how about as x goes to negative infinity? Now let's talk about that. Ready? Let's talk about this now as x goes to negative infinity. Again, if I start putting numbers in there that are going to negative infinity, now we're talking about okay, so what's happening here, guys? It's getting smaller again, and it's approaching a 0 again, except this time from the negative side, right? But they're still approaching 0. Do you agree with that? Do you agree? The limit is still 0, just you're approaching 0 from the left side now instead of the right side. But the limit is still 0. Got it? Okay, so that's where I got that from. Okay, so what does this mean? This means this graph, since those are both 0, then you have what? 1 what? 1 what? Horizontal asymptote. And what is it? It's y equals 0. So the graph of that function will have 1 horizontal asymptote. So what I just showed you now is how to find the horizontal asymptote. So in the future, on my test, on the homework tonight, on the AP test, they give you a function, they say find all horizontal asymptotes. What are you guys going to do? You're going to find the limit of that function as x goes to what? Infinity and negative infinity. Okay? And if you get a number for either of those, that's where your horizontal asymptotes are. In this case, they both equaled 0, so I had 1 horizontal asymptote. What if those equal 2 different numbers? Then you'd have what? 2 horizontal asymptotes, right? What if neither of them equal the number? And you have no horizontal asymptotes. Got it? Easy? Okay, let's do another example. Don't worry, guys. They won't all be this nasty. Okay, just bear with me. I intentionally typed up all the steps here so you don't have to worry about writing all this down. I'm going to fly through it, though. Ready? Okay, what do I want you to do? I'm giving you a function. I'm asking you to find all what? Horizontal asymptotes. So what am I going to have to do? Quick. Find the limit of that function as x goes to what? Infinity, and then again as x goes to negative infinity. Okay, so here we go. So I'm finding those 2 limits, correct? All right, let's talk about the first one. By analysis, as x gets bigger, what's happening to that polynomial? It's getting bigger, isn't it? What about the bottom polynomial? It's getting bigger. So can you really say what's happening to the whole function if the top's getting bigger and the bottom's getting bigger? No, you're kind of stuck. Okay, so the numerator and denominator are both getting larger, so I really don't know what that limit is. So I'm going to need a new method to find that limit. Are you ready? Okay, so there's a trick here. The trick is to divide the numerator and the denominator by the largest power of x that you see in the denominator, and then simplify and go from there. Are you ready? Okay, so here's what I did. What is the highest power you see in the denominator? Quick. X squared. So what I did is I divided everything through by x squared, and then I simplified it to this. And then I used my limit laws to split it up into those 4 separate limits. What's the limit of 3? Quick. 3. What's the limit of 1 over x as x goes to infinity? 0, just by analysis. What's the limit of 5? 5. What's the limit of 6 over x as x gets bigger? 0. And so what's my limit here? 3/5. Following me? Okay? Now, I'm not going to go through it, but if I do the same thing, as x goes to negative infinity, I'm going to get 3/5 again. I didn't show you the steps, but it's the same process. And so what do you think, guys? Those are both 3/5, so I only have what? One horizontal asymptote on that graph. What is it? 3/5. Now hold on a minute, guys, before you turn the page. That's a lot of work, isn't it? The good news is there's a much, much, much easier way. Okay? So you're not going to have to do that. But I wanted to do it anyway. Okay? So, last page. Ready? All right. So instead of doing all that, I'm going to teach you some shortcuts that will always work. Are you ready? All right. So first of all, you got to know, first of all, when to use these shortcuts before I teach you the shortcuts. So the 3 shortcuts I'm about to show you can only be used when you're taking what? When you're finding these limits, right, as x goes infinity or negative infinity for a, by the way, f is not a polynomial. I should say f is a rational. Sorry about that. Okay, so f is a rational function in the form where you have a polynomial over a polynomial. Okay, so if you have a polynomial over a polynomial and you're trying to find the limit of those types of functions as x goes infinity or negative infinity, that's when you can use these 3 shortcuts I'm about to show you. Are you ready? Are you ready? Almost done, guys. Hang in there. What does this mean if n is greater than m? Well, that means if the what? If the denominator has a higher degree than the what? Numerator. Think about that. If you got a polynomial over polynomial and the bottom one has a higher degree, won't it grow faster than the top if it has a higher degree? Won't it? As you start plugging in x's that are going to infinity, won't the bottom grow faster than the top if it has a higher power? So using common sense, what happens to a fraction if the bottom is growing faster than the top? It's going to get smaller and smaller and smaller. It's going to go to what? 0. So there you go. So if the bottom has a higher degree than the top, those limits will both be 0. Does that make sense? Okay. Let me back up a minute. Look at that example 8 I did a minute ago. Let's look at the degrees. What are the degrees there, guys? Look, they're both what? They're both what? 2. And what did the limit turn out to be? 3/5. Where do you think the 3 and the 5 came from? The leading coefficient over the leading coefficient. So that's shortcut number what? 2. If they have the same degree on the top and the bottom polynomial, these limits will always be what? Leading coefficient over what? Leading coefficient. That's shortcut number 2. Very easy. Just remember it, right? Okay, now the tricky one. The tricky one is when what? When the top has a higher degree than the bottom. Well, again, use some common sense, guys. If the top is growing faster than the bottom, what's happening to the entire fractions? They are getting bigger and bigger and bigger. So the limits will either be what? Infinity or maybe what? Negative infinity. So the hard part is figuring out which one of the 2 it is. Okay, and that's basically what the rest of this is explaining. So let me go through it. Okay, so how do I decide then if it's infinity or negative infinity in this 3rd scenario? Well, I'll explain it. Ready? All you got to do is look at the what? Look at the first terms to decide if each is positive or negative. So let me explain with an example. So for example, suppose I'm trying to find the limit of this as x goes to negative infinity. And again, why did I put dot, dot, dot? Because the other terms don't matter. Only the what? Only the leading terms. Why are the only ones that matter? Because those dominate, don't they? Don't the biggest terms dominate what happens? Right? As you're going out to infinity or negative infinity, that's why the other terms don't matter. So suppose this first term is that. Suppose the bottom first term is that. Let's analyze it. Ready, guys? I'm finding the limit as x goes to what? Negative infinity first. What happens when I stick a negative number into 2x to the 5th? Well, what happens when you raise a negative number to a 5th power? Is it positive or negative? Negative. And then I multiply by a positive 2, it's still what? Still negative. Okay, how about when I stick a negative number into negative 7x cubed? Well, how about when I stick it into x cubed? When I cube a negative, I get a negative. But when I multiply a negative by a negative 7, it'll turn positive. And so you'll have a negative over a positive, right? as you go out to negative infinity, right? And so what's a negative divided by a positive? A negative. So guess what? So that limit is what? Negative infinity. So that's how you figure it out. Okay? We just have a couple more examples and we are done. Here it goes. Stay with me. Fill this in. Real quick, guys. Can I use a shortcut there? Yes or no? Yes. Because I'm taking a limit as x goes to what? Infinity or negative infinity, where I got a polynomial over a polynomial. Okay, so real quick. What's higher, the top degree or the bottom degree? The bottom, which means the denominator will grow quicker than the top, which means the fractions will get smaller and smaller. What's this limit? 0. Easy, isn't it? No work required, just a little bit of thought. Okay, next one. I don't like that. Why don't I like that? Because it's not in what? It's not in standard form, so please switch that around, okay? All right, now, looking at that and that, what are the degrees? They're both what? 2. So when you're finding a limit as h goes to infinity, and you have a polynomial over polynomial with the same degree, what is the limit? The limit in these cases is always going to be what? The what? Leading coefficient over the leading coefficient. Everybody agree it's negative 3/5 then? Easy. Next one. You tell me, what is it? You guys tell me, what is it? What is it? 0. Why? Because the bottom has a higher degree. It's going to go faster than the top. When you have a bunch of fractions, right, where the bottom is growing faster than the top, the whole fraction is going to get smaller. It's going to be 0. Got it? Next one. All right, this is one of those tricky ones, because what do we have? The top is what? Higher degree than the bottom. So I know this is either what? Negative infinity or positive infinity. I got to figure out which one it is. How? Well, this is what you look at. I'm only going to what? Positive infinity, so I look at that and that. So as x goes to positive infinity, I'm only going to be plugging in positive numbers eventually, correct? Okay, so if I'm plugging positive numbers into 2x to the 5th, it's going to be what? Positive. Okay, how about here? Negative. And so what's a positive divided by a negative? Negative. So guess what? This limit is negative infinity. It's that easy. Got it? All right, so get E. Which has the highest degree? Top or bottom? Top. So again, this is either what? Negative infinity or positive infinity. Again, how do I figure out which one it is? Yes, question? Yeah. No. But this, remember, it says x goes to positive infinity. So if I'm going to positive infinity, eventually I'm only going to be plugging in positive numbers, right? So that's what I'm looking at. Got it? Okay. All right, now this time I'm going to what, though? Negative infinity, so be careful. Okay, so I'm going to be plugging only negative numbers into there eventually, and only negative numbers into there. Be careful. So when I plug a negative in there and cube it, is that positive or negative when you cube a negative? Negative, but then you multiply by a -4, making it positive. Okay, then how about when I stick negative numbers into 3x squared? Well, when I square a negative, I get a what? Positive. Then I multiply by +3, that'll be what? Positive. What's a positive divided by a positive? Positive. So guess what your limit is? Positive infinity. Isn't this easy? All right. Hold on. Hold on. Hold on, guys. Ready? Does this technically fall into this category? No, because the bottom is not a polynomial due to that square root. However, can you kind of think of it as the square root of x squared, kind of, even though you're not allowed to break it up like that? Is it kind of like that? Yeah. So if you think of square root of x squared, that knocks the degree in the bottom down to what? Down to what? Yeah, x to the first. So technically, the top and bottom have the same degree, technically, don't they? And so what is the limit supposed to be in that scenario? Leading coefficient over leading coefficient. So what's the leading coefficient on top? 1. What's the leading coefficient if you, again, even though you're not allowed to split that up into the square root of 9x squared plus the square root of 1. Even though technically you're not allowed to do that, you can kind of think of it like that. So what is the square root of 9? 3. So isn't that leading coefficient 3 technically? All right, now wait. So I'll tell you right now, we're not done. This limit is either 1/3, but it might be negative 1/3. That's the only extra thing you got to think about. So how do I decide if this limit is positive 1/3 or negative 1/3? Well, I'm only going to positive infinity. So as x goes to positive infinity, that will be what? Positive. This will be what? Positive. You'll have a positive over positive, so it's got to be what? Positive 1/3 rather than negative 1/3. Is that clear? Okay, so there's a little extra trickiness there. All right, 3 more easy ones and we're done. Are you ready? All right, these are different. Example 10 is different. I'm just going to use what on each of these? Circle that. I'm using what? Analysis. Okay, so here we go. So I want to find that limit, and it doesn't fit anything I taught you last time or today. Okay, it does not fit any of the scenarios, does it? No? So let's just see if we can do it by analysis, by common sense. Are you ready? Okay, don't my limit laws from last time allow me to split that up into those 2 separate limits? Don't they? All right, what's the limit of 5? 5. All right, now you're going to subtract this limit. What is the limit of 4 times x as x goes to negative infinity? Think about it. Common sense. You got positives times negatives that are getting bigger. So the product for x will go to what? Agree it's negative infinity? Okay, so what is 5 minus negative infinity? In other words, you're taking 5 and you're subtracting numbers that are going to negative infinity. And so on. What's going to happen to these numbers, guys? What's going to happen to these numbers? They're going to get what? They're going to get bigger and bigger and bigger. What's this limit? Infinity. Got it? I mean, so you can kind of think of it like that. So my answer is infinity. Do you understand what I did there? Easy, right? Okay. So the ones that don't fit, all the tricks I've taught you, sometimes analysis is all you need. Got it? Sometimes you might need a table and a calculator. I'll give you that on those problems on the test. So no matter what limits I throw at you on that upcoming test, you should be able to handle them, right? Just got to know all your different scenarios and all your different tricks, right? All right, this one, guys. Analysis. Well, first of all, can I split it up? Can I? Yes. According to my limit laws, I can split it up into 2 separate limits and then subtract them later. All right, as x gets bigger, what happens to x squared? Gets what? Gets what? Bigger. So the limit there is what? Infinity. What's that limit? Quick, by analysis. Quick. Come on. Infinity. Now, is infinity minus infinity necessarily 0? No. Because one might be going infinity faster than the other. So please don't say that infinity minus infinity is 0, because it's not. It might, right? Got it? Because one might be going infinity faster than the other. Okay, so that logic didn't work. So let's try something else. What might I try instead? Well, can I factor out an x? Can I? Sure, and then I've got that limit, right? Do my limit laws allow me to split that up into the product of the limits? Sure they do. So now I'm looking at that limit times that limit. What's the first limit? As x goes to infinity, x will go to what? Infinity. What about the second limit? Infinity. Now, is it safe to say that infinity times infinity is infinity? Think about that. You're multiplying 2 numbers and they're both getting bigger. What's happening to the product? It's getting what? Bigger. So that time, that logic did work. Here's another way you can do it. What's going to, let's back up to here. Which one's going to infinity faster? The x squared or the x? The x squared. So if those numbers are getting faster than the numbers you're subtracting, what's going to happen to the whole numbers? They're going to get what? Bigger. And so it's going to be what? Infinity. So that's another one. There's a third, right? I'm sorry, that's the second way you can do it. Okay, guys? All right, one more. One more. These look like the toughest ones, but they're not. Didn't I say you better memorize that because it's going to keep coming up over and over and over? What does the graph of that function look like? Quick. 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 E to the 0 is, where's my red? Oh, here it is. Where's e to the 0 is 1. And then what else did you have to memorize? That there's a what? A horizontal asymptote here, and then what else? That the graph just rises from what? From left to right, like that. Yes? Agreed that that's what that memorized graph looks like? Okay? Okay, so then how would you handle E then? What does the plus 1 do to the memorized graph? It moves it what? 1 up. So let me draw that graph for you. Are you ready? So won't that asymptote move up to there? And won't the 0.01 move up to there? Yes? Okay, so just looking at the graph of the function, you should all be able to look at that function and tell me what the limit is. As x goes to negative infinity, you're talking this, right? X is going here. There. What are these y values approaching? Yeah, they're approaching that horizontal asymptote, so the limit is 1. See how easy it is if you just use the memorized graph and then translate it and just look at the graph? Easy. And you probably thought that was going to be the hardest one, didn't you? It was the easiest one. Okay. What about this? What does the graph of y equals e to negative 2x look like? Well, the 2 doesn't really change anything, but the negative does what? Flips it over the y-axis. So what does that graph look like? Hold on. So does the 0.01 change? No. Does the asymptote change? No. But instead of rising from left to right, it what? Falls from left to right like that, correct? So looking at that rough sketch, what is the limit as x goes to positive infinity? As x goes to positive infinity, the y value is approaching what? 0. By the way, what would be this limit as x goes to negative infinity? Infinity. Right? Just by looking at the graph. Okay, guys? Yes?